China has made an impressive leap in nuclear fusion, once again taking center stage in the pursuit of a clean, limitless energy source. The scientists working on the experimental advanced superconducting tokamak, EASD, frequently referred to as the artificial sun, have made a significant breakthrough in their mission to unlock the potential of nuclear fusion. This remarkable achievement brings the world closer to a future where energy can be produced in ways that are not only abundant but also cleaner and more sustainable than the traditional methods we rely on today. The East Reactor, located in Hefei, Anhui Province, recently achieved an extraordinary milestone. It successfully sustained plasma at temperatures exceeding 70 million degrees Celsius for more than 17 minutes. This is a momentous development in fusion research. To put this into perspective, the core of our Sun burns at a temperature of around 15 million degrees Celsius, so the East Reactor was nearly 5 times hotter than the heart of the Sun. This incredible achievement represents a critical leap in the effort to replicate the power generation process of the Sun here on Earth, bringing us one step closer to mastering fusion energy. The science behind nuclear fusion is the process that powers the Sun and other stars, releasing vast amounts of energy through the fusion of atomic nuclei. It is distinct from nuclear fission, the process used in current nuclear power plants, which splits atoms and produces radioactive waste. Fusion, on the other hand, has the potential to be much cleaner, with virtually no harmful emissions or long-term radioactive waste. Instead of using uranium or plutonium, fusion relies on hydrogen isotopes, such as deuterium and tritium, which are far less harmful and are abundant in nature. Deuterium, for example, can be extracted from seawater, offering a practically unlimited source of fuel for fusion reactions. The power that could be derived from nuclear fusion is staggering. A fusion power plant could produce virtually limitless energy without the environmental drawbacks of fossil fuels. Moreover, unlike renewable sources like solar and wind, fusion doesn't depend on weather conditions or time of day, making it a reliable energy source available 24/7. The ability to generate this level of energy cleanly and continuously could revolutionize how we power our world, drastically reducing the need for coal, oil, and natural gas, and potentially eliminating the environmental damage caused by fossil fuel extraction and consumption. However, the path to achieving a functional fusion reactor has been fraught with technical challenges. One of the most difficult aspects of fusion research is maintaining the extreme temperatures required to sustain the reaction. The plasma, an electrically charged, superheated gas that fuels the fusion process, must reach temperatures of millions of degrees to induce fusion. At these temperatures, the plasma is incredibly unstable and must be confined using powerful magnetic fields. Any instability in the plasma could cause it to cool down, or even escape the magnetic confinement, halting the reaction entirely. The breakthrough achieved by the East Reactor is crucial because it demonstrates that it is possible to maintain plasma at such extreme temperatures for an extended period, paving the way for the eventual stabilization of fusion reactions in a power plant. The global race for fusion energy. China's progress in nuclear fusion has placed the country among the front runners in the global race for fusion energy. Alongside China's East Reactor, other ambitious fusion projects are underway in countries around the world. One of the most prominent of these is the International Thermonuclear Experimental Reactor, ITER, in France, a multinational collaboration involving 35 countries. ITER aims to build the world's largest tokamak, a magnetic confinement device that will be capable of sustaining fusion reactions on a larger scale. If successful, ITER will demonstrate the feasibility of using fusion as a reliable and sustainable energy source. In the United States, the Spark project, led by the Massachusetts Institute of Technology, MIT, in collaboration with private industry partners, is working on creating a compact and efficient fusion reactor that could be operational within the next decade. The goal is to make fusion energy more accessible and commercially viable by developing smaller, more cost-effective reactors. Spark's approach involves utilizing cutting-edge materials and advanced superconducting magnets to improve the efficiency and stability of fusion reactions. In addition to these large-scale projects, several private companies are also making strides in the field of nuclear fusion. Companies like Helion Energy, Commonwealth Fusion Systems, and TE Technologies are exploring innovative fusion reactor designs and technologies, aiming to bring fusion energy to the market more quickly. By using high-temperature superconductors, better magnetic confinement techniques, and novel fuel cycle concepts, these companies hope to accelerate the timeline for commercialization. They are also focused on reducing the cost of fusion reactors and improving their efficiency to make them competitive with other forms of energy generation. Historical developments and challenges. The quest for nuclear fusion has a long history, dating back to the early 20th century. Early experiments and theories about fusion were largely theoretical, and it wasn't until the 1950s that the first serious attempts to replicate the fusion process in a laboratory setting were made. In these early years, researchers focused on developing magnetic confinement devices such as tokamaks and stellarators. These devices use strong magnetic fields to contain the superheated plasma and prevent it from touching the walls of the reactor, which could cause it to cool down and lose the energy required to sustain the reaction. Since those early days, fusion research has made tremendous strides. Plasma confinement and stability have improved significantly, and much work has been done to extend the duration of fusion reactions. However, several significant hurdles remain. For one, the extreme temperatures required for fusion reactions make it difficult to find materials that can withstand the heat and radiation produced by the plasma. Additionally, scientists still face challenges related to the breeding and management of tritium, one of the key isotopes used in fusion reactions. Tritium is rare and must be produced in the reactor, adding a layer of complexity to fusion energy production. Researchers are also exploring alternative fuel sources, such as helium-3, which could offer even greater efficiency and safety than tritium. The potential impact of fusion energy. The potential impact of successful fusion energy technology is nothing short of revolutionary. While commercial fusion energy is still likely years away, the recent breakthroughs in plasma confinement and temperature stability bring us closer to a future where clean, limitless energy could power everything from homes and industries to entire cities. The environmental benefits of fusion energy are enormous. Unlike fossil fuels, fusion does not release harmful pollutants like carbon dioxide, nitrogen oxides, or sulfur dioxide into the atmosphere. This could dramatically reduce global greenhouse gas emissions, helping to mitigate the effects of climate change. Beyond its environmental benefits, fusion energy could have profound geopolitical implications. Countries that currently depend on fossil fuel exports may need to adjust to a new energy economy, while regions with limited access to conventional energy sources could become self-sufficient. This would fundamentally alter the global balance of power, as nations could rely on fusion energy for their own domestic needs, reducing their dependence on oil and gas imports. Fusion energy also holds the promise of revolutionizing space exploration. Because fusion reactions produce vast amounts of energy from relatively small amounts of fuel, fusion could provide a nearly limitless power source for deep space missions. This could make long-duration space travel more feasible, opening up new possibilities for exploring the far reaches of the solar system and beyond. The road ahead. The road to commercial fusion energy is long and filled with challenges, but the recent achievements in nuclear fusion research give reason for optimism. As research teams around the world continue to push the boundaries of what is possible, the dream of harnessing the power of the stars may soon become a reality. With sustained efforts from governments, scientists, and private companies, we are moving closer to the day when fusion reactors will be a practical and scalable source of clean energy. However, there is still much work to be done. The transition from experimental fusion reactors to fully operational power plants will require substantial investment, infrastructure development, and regulatory frameworks. Governments, research institutions, and the private sector must collaborate to accelerate progress and ensure that fusion energy becomes a viable option for powering the future. If these efforts succeed, the world may soon experience an energy revolution unlike anything seen before. Fusion energy promises to provide a cleaner, more sustainable, and virtually inexhaustible source of power that could transform the way we live, work, and interact with the planet. The age of fusion energy is on the horizon, and it could offer a brighter, more sustainable future for generations to come. For oh many